Yeah, so I got a bit of flu this week, so let's see how I'm able to. Sorry.
Cold Austria.
Cold Austria. Yeah, actually, I arrived here Sunday. It was like all stormy, wet, cold. Feels like plus 6 degrees in Celsius. So like. We had much better weather. Yeah, so indeed. So Finland, Mikko Ylinen from Finland, Intel. I've been working on confidential computing, cloud native technologies for some time now, and in the intersection of those two, I'm also one of the maintainers for the confidential containers project. So that's one of my main work areas these days. You can find me on GitHub mostly where all of the confidential containers work is happening. What I'm going to be talking about today, it's not confidential containers related, although I have a few samples that I'm using confidential containers building blocks. But my topic today is just like how we could use the Linux existing Linux Keyring services to hide some of the attestation related functions from applications, making it easy for the applications to consume confidential computing or adopt confidential computing without them applications themselves having to know much about like what is happening with the attestation. It's also I've also been part of a few conversations, discussions around whether we would actually have to have application APIs for applications to consume, for the applications themselves to produce evidence to take part in the attestation. And my discovery was like, hey, we have this Linux Keyring that seems to be providing quite close services that kind of fulfill this API, TEE, evidence API topic. But then once I've been talking about that topic, I've also got some feedback that, hey, okay, that sounds good, but it always depends on the use case, so it may or may not work. So in my talk today, I'm also hoping to give you like a few sample use cases where I think that this actually demonstrates that the potential to be functional. And now that I'm losing my voice and the audience is pretty experienced and you know, we talked about the RATS architecture, I'm actually going to skip a few of my slides. So this is what I had planned. So talk a bit about confidential computing one-on-one, so we all know what that is about. We know the RATS architecture very, very well. So I don't need to go into the details of any of the different attestation roles and topologies. So what I'm going to do next is just I'm going to skip those and go directly to the introduction of what this Linux Keyring is about and what it actually offers or could offer for applications. And then I have a couple of use cases, like I said, so demonstrating some of the capabilities. One thing that I also forgot to say is that my talk is very, very different from what we have seen today. So it's like a bit of low level. So I hope we also have some developers in the room or people who are more like more like a hands-on. I thought I had this skipped. So this is what we all know. So what I'm talking about is mostly around attesters, verifier, relying party. We know the different RATS defined attestation topologies. The reason why I have these two main topologies here is that the two use cases that I'm going to be talking about one kind of matches this background check topology, and the other one is sort of like a building block for this passport mode. But like I said, so I'm going to skip all of this confidential computing one-on-one intros and go to the keyring part. What this Linux keyring is fairly well documented on the manual pages. It was originally implemented for in-kernel services to get different types of security data stored within the kernel itself. Things like certificates, keys, various types of tokens. But we have also seen different applications, use cases that are applications that are using the in-kernel storage to store the secrets. So there are APIs for the applications to get their own secrets or get their own data stored into the kernel keyring. And the data that gets stored is rather opaque. Each key in the keyring is defined by the key ID and what type of key it is. Then it's also, in addition to the ID, described by a description, like a text format description that is being used to search for certain keys in the keyring. And what is also nice about these keys and what the kernel services offer is that it offers quite nice access control capabilities, things like how long the key is being valid in the keyring, and reference counting, like who is using each key and things like that. The keys, they have types. The keys, they have types. What I've found and what I'm going to be demonstrating later on is this user type key. There are also other interesting types like asymmetric key type, encrypted key type. One commonly used is the trusted key type, which is sort of anchored to the on device or on platform the TPM functionality, but that is maybe not so well suited for different TEE environments that do not have things like VTPMs attached. But the keys can also have key ring. There's also a key type called keyring, and what these key rings are about. So it's basically a mechanism to anchor the key lifetime to something more persistent. On the code snippet, there we can see a sample of a root user's session keyring and then all the various key types that are being attached to this root user's session keyring, and that's basically the mechanism how some of these keys are anchored to some anchor point, and it's in this case it's the user's session keyring. But there are also other quite nice anchor points. For example, a key can be attached to the lifetime of a process, or even like going into the more details, that the key can also can only be attached to a thread within a process. So only that particular thread within the process has certain permissions to use the key. So quite flexible mechanism to control who has access to some in-kernel data. It can be a secret, for example, or a token, I'm showing shortly. And I already briefly mentioned, so the APIs to control what gets into the kernel, what gets into the keyring, they are like syscall based, giving like a stable API to actually consume this type of functionality from the application perspective. What I'm talking about, and like this hiding attestation, is this whole idea is built on this key request service, request key capability, and how that works is what I'm going to explain next. So a very basic, simple function call or system call called request key. This is not the syscall definition. This is a wrapper from the key utils library. Basically, the user of this function would just like specify that, hey, what is the key type the application is interested in, what the description is. It's the free text description of the key. Some additional call parameters are being passed into this callout info parameter, and then some keyring, destination keyring is basically where this key that is being requested gets anchored to. And then once this function is being called, the kernel tries to search for the key within the keyring, and then returns to the result. If it's found, if it's not found, it returns an error. But there's a quite interesting capability is that if this callout information, callout info parameter is not null, the kernel has this capability that, hey, let me also search for a provider of this key from the user space, and this call out is being hooked to this request slash spin request key binary, then that then has its own mechanism to search for additional key providers. And examples what these key providers could be, and then again in the context of this confidential computing, we could have a key provider plugin attached to this request key, callout information to get whatever is the requested key type about. It could be a secret from some key broker service, HSM type of service, or like I'm demonstrating soon, it could also be an attestation token from a verifier. Like I said, like I mentioned in the very beginning, I'm using some of the confidential containers building blocks to demonstrate this functionality. In confidential containers, in addition to all of the attester components that we are developing for the confidential VM side of things, we also have a reference. We have a component called trustee, which is like both a verifier and a relying party, in a sense that you can request evidence verification from this trustee component, but it also serves various endpoints to request secrets. So it's also kind of like a relying party application returning secrets based on like a successful attestation. And then mapping this confidential containers functionality to this request key example, so we can have an application that is requesting for a key using this request key function. The kernel cannot find it. It sends out a callback to the user space, and then I have in this Coco example, I have this up call hooked to something that we have in Coco called key broker client, which then connects to the trustee key broker service to get the attestation or get the secret provisioned. The trustee KPS, the trustee component returns the token or key depending on the use case back to the upcall function and then instantiates the key, and that's how the application that originally requested a key or an attestation token gets to read the token, but in a way that the application is completely transparent to how it got attested or how the secret got into the TEE. Two use cases, actually three, but that's more like a bonus use case. But one use case is with this Lux encrypted block device encryption. And why that is relevant for confidential VMs is that if you have data that you need to store within the virtual environment to some block device, we know from the trust model that everything that is outside the confidential VM, including all the VMM components, are outside the trust boundary, and oftentimes systems using VirtIO functions are something that they are like part of they are outside the trust boundary. So that's why it's important if you're storing some temporary data within a confidential virtual machine environment, you encrypt your data before it gets committed to the virtual block device. That's just one example. There could also be other examples or use cases where this Lux de-encrypt based partitions or block devices are used. But long story short, it is possible for the Lux crypt setup to use this functionality that I described. At the moment, it doesn't work in a way that in an ideal way. It basically, the crypt setup doesn't use this crypt setup doesn't use this call out information for anything, so it simply sets it to null. But this can be work around it quite easily in a way that when the user issues the keyctl request commands like by hand, and it is configured to use the Coco key broker service, that the key gets automatically, transparently provisioned into the Keyring so that this crypt setup can work. And this is, like I said, well, this kind of demonstrates this background check functionality. I've also done a bit of experimentation here that it's fairly easy to get this crypt setup modified in a way that this call-out information is non-null, and it allows us to automatically use this call-out mechanism to get the encrypted block device opened with attestation, with a key or with a passphrase actually being stored on a key broker service and then pulled into the confidential VM using attestation. Looks like I'm missing something that I wanted to add here, so I've also proposed this particular small change to the crypt setup upstream project, but they haven't really gotten back to me on that yet, whether they think it's useful or not. Another use case I have demonstrating this kind of a passport mode where the application needs to get an access, or where the application needs an attestation token. And the same mechanism using this request key provider can be used so that instead of the call-out provider talking to some key broker service, it can call out to some verifier that returns an attestation token back into the keyring. And with using some of the kernel keyring services, it's possible to make this call-out provider intelligent in a way that it can, for example, it can read the token parameters and automatically set the key life cycle within the keyring based on what the token lifetime is, what the verifier has set for the key, and then automatically make the key, or in this case it's the token to expire. And then if the application, and then it also helps the application. The application doesn't need to know much about like when to request a new key, so they can the application can, or when to request a new token, for example. The kernel can do that automatically or behind the scenes. In the code snippets, I just have a simple demonstration of this functionality that the user can call Coco token, maybe add some additional parameters to the call. It gets the key back, or in this case, the token back, and then we can observe or read some of the token parameters, like the signer of the token or what the TEE environment is. But this is just for example purposes. I've also done a bit of experimentation using this asymmetric key type, which to me at least sounds fairly interesting use case in a way that if your key type is an asymmetric key type, you get this asymmetric key provisioned into the keyring. But how this keyring functionality works is that with this asymmetric key type, the private key part of the key is never going to be possible. Even the user space won't be able to read the private key part of this asymmetric key, which is quite nice in a way that the application doesn't need to worry about keeping it in secure. It's just in the kernel space, and it can be used for things like code signing, for example. That's what I've been experimenting here. That pretty much concludes my talk. So just like I said, wanted to kind of demonstrate this type of capability. Hopefully, it's useful for some cases, and if we ever get back to this. Do we need an attestation API? This has some potential, at least I think it has some potential to kind of just hide some of the attestation complexity. And one other thing that I think this is beneficial is that we can control what goes into these call-out providers, so we can write them like using some memory safety languages like Rust, and then we can have our applications written in whatever programming language we may want. We have the syscall-based interface to get what we need, like an attestation token or some key, and the applications don't need to get involved into the attestation process. So, yep, that's pretty much what I wanted to say. So if people are interested in giving this a try, I've made all of the key CTL or the keyring configurations available on my GitHub gist here. It's mostly using the Coco components unmodified, so it's just a matter of just following following the configuration that I made available in the gist. So it's quite easy to get your hands dirty if this use case sounds interesting.
Questions, go with it.
I was just wondering, it assumes that your trusted execution environment has its own guest kernel, right? Because so it would apply for Intel TDX. If I would apply that concept on an Intel SGX, it would be screwed because then my surrounding would have the secret, which is just the test.
That is true. Yeah. So you need to have a.
In case of Cocoa, it's clear because right now the implementation ways with the pure pods and with the KVM-based solutions, we have it. But I just wanted to clear it. It's the guest kernel where you need to apply.
Guest kernel. Yep.
On the host kernel, I don't know whether from a security perspective you run into trouble.
Yes, and then well, SGX could work if the library OSs would implement the syscalls. I've actually wondered about that myself. So it could be possible to have something like CCC's Chromium library OS to implement this particular syscall functionality, that if you have an application that issues this particular syscall, the library OS could try to handle that request somehow. But yes, so it is. It's very much true that this depends on. But like that's basically it was like mentioned in the title of my talk that this is specifically for the confidential VMs. One thing though is that with the Cocoa setup that we have is all of the TEEs we support, in particular the virtual machine based TEEs. We have that vendor specific abstraction covered in Cocoa. So that's basically what this comment tries to say here, is that this KPS client, in this case it's just the KPS client tool that I was using for demonstration purposes. It can be built in a way that it just works on any of the confidential VM TEEs that are available.
Because I saw this on Monday and we had a conversation afterwards, and I noted that unless you already had the ability to make an encrypted connection outside, then all of the communications, including that key, would be visible. But the Cocoa setup does provide you with that, so it's already there.
I mean, I'm familiar with the confidential container project. So
I wasn't.
I just wanted to make sure that I got it right.
Yep. Yeah. So SGX not covered, but all of the confidential VM TEEs we have covered.
So it's also covered, I could assume, by the confidential container secure execution implementation. I could check it.
Yes. Yeah. And like I said, so if you just take what I have here, it should work. So it's I probably don't want to get into the demos, but it's basically all of the for example it just issues the KPS client to my trustee KPS URL and then gets the key instantiated. I can show you a live demo. I wasn't planning on, even though I had prepared it. But so the bottom side of this is the KPS or the trustee console log. And then when I'm issuing this request key function, it does all the attestation behind the scenes, and you saw the activity happening on the trustee side, and that's how we got the key. And then the application. Oops, yeah, well, this is the JWT token here, so. I can print out the full.
Can the people not parse that on their own? I don't know.
It's B64 input, no problem. We can't read that, right?
Exactly, that's why I'm saying that people in the room can't.
Automatic decoding in your head. So it's basically the COCO token that's part of the keyring. Just
What is the nonce? Where's the
the nonce in this case is it's part of the confidential containers. There's this KPS protocol, and it is this nonce comes from the relying party, the KPS, and then it gets added into the quote, and then it's been verified. So there's a nonce, but that's part of the protocol. I've been thinking of implementing this for this token provider mechanism using this keyring for some other verifier services. But that's something that I don't have available just yet. Mostly curious to hear people's thoughts on if it's useful to explore further. I would very much like to hear comments, use case ideas to understand like how to.
Well, I'd love to know if there's ways of implementing it when you don't have confidential material already available to you, so you could use it for setup. But I'd have to think quite hard about how that would work.
I would need to cross-check, but we have something which is called the basic encryption and a crypto facility. And there you actually can have, from your hardware security module, being for your logical partition, something like that. And then you have Linux calls where your data in rest and data in flight, transaction locks keys, and what you mentioned, will be basically leveraging these keys, and you don't even have them in the kernel key. So, but generally speaking, like the approach I already selected James, you probably know, to see where I think I saw it.
Mr. Bottom.
James Bottom.
Oh, different James.
Yeah, okay.
Right, thank you.
Thank you. I think I managed with my voice.
You did very well done, yeah.